All right, so this is 8G. So as a ring seen from above is pulled on by 3 forces, the ring is not moving. Right, so we can say that, well, my net force in the y direction is 0. And well, how big is this force F, right? So we know that, well, we need to first figure out all my forces in the y direction. Well, what are my forces in the y direction here, right? And again, we talked about this in class. Well, we can separate a force, a vector, right? We can separate a vector into not only a y direction, but we can also separate it into an x direction. Because we can do that, right? We can do that. So there's a tension here in the x, and there's a tension in the y. And so this is actually my full tension of 10 newtons. And here's what I like to do, right? So clearly, we have this, we have a triangle. I'm gonna move my tension in the y over here, right? So we can actually get an actual triangle, and we have an angle here. So the first thing we want to do, again, to solve these kinds of problems, to figure out, well, what is Ty, we kind of have to use trig. Here's like how I like to think about trig, right? Here's how I like to think about trig. When we do trig here, I like to think of sine as opposite. I like to think of cosine as adjacent, right? So already from that point on, you can pretty much solve all problems. So where is Ty in reference to your angle? Is Ty adjacent or opposite to this angle right here? Well, Ty is opposite to this angle, right? It's opposite to this angle, which means that this angle right here, right? If we were to solve for this side would be my hypotenuse T, all right, sine, because it's opposite, and then theta. That would be that. So this y side here, because it is opposite, I'm going to use sine, and I'm always going to put my hypotenuse in front of the sine there. I'm always going to put the hypotenuse in front of the sine. So Ty is equal to T sine theta. And Tx, because Tx, T sub x is adjacent to this theta, because of the adjacent, I'm going to use cosine. And I'm going to lead it off with my hypotenuse, cosine theta. And that's something you can always do, right? This is something you can always do here. I would definitely get used to memorizing this. Right? I would definitely get used to memorizing that. So now we figured out our y, right? So our y, our tension along the y-axis exerted by each of these ropes, each of these, it is ropes, right? Each of these ropes is T sine theta, right? So the tension exerted by this rope and the y direction is T sine theta. And same thing on this side. So the tension along the second rope is also T sine theta. So if we do our net force, right? If we do our net force along the y direction, well, we have our vertical forces upward, right? We have vertical force T sine theta plus T sine theta, right? Our vertical force is upward, minus our force downward. And our tension here is 10, so T is 10, right? My tension force is 10. So we can further simplify this by saying, well, by saying, I'm trying to erase it right now because my app is bugging out. My app is bugging out and it's extremely frustrating. I'm gonna pause the video until it comes back again. All right, so now back to this problem. So we were at Fy is equal to T sine theta plus T sine theta minus my force to gravity downward. All right, so Fy here is equal to 2T sine theta minus F, because right, you can just add these up. And then you can say, well, 0 is equal to 2T sine theta minus F, and then you add F on both sides, right? And then you get F is equal to 2t sine theta. Tension here is 10, so essentially you're doing 2 times 10 sine theta, and so then you get 20 sine theta. All right, 20 sine theta. So the answer here is E. Answer is E. H, 8H. So we have this diagram here. So a ball weighing 50 newtons is pulled back by a rope at an angle of 20 degrees. And the question says, well, what is the tension in the horizontal cable that's pulling this ball back? So again, the object is in equilibrium, which means that, well, my net force in the x direction should be 0 here. Okay, and we also know that, well, my net force in the y direction is also 0. And so we want to find out tension here. I'm going to call this tension 1. And there's this tension, the rope here also has a tension, right? The rope also has a tension, and there's a horizontal vector this way, right? So we're gonna call that, I'm gonna call this second rope tension 2. And so this is the tension in the x direction of the second rope, and this is tension in the y direction of the second rope. So tension to y along the y-axis, right? So along the y-axis. So now we have to figure out, well, what is T2x, right? What is the tension along the x-axis here? Because if we kind of look at our net forces here, we'll see that, well, my horizontal force, all my horizontal forces here is T2x along the x direction minus the tension of tension rope 1. So my right force here horizontally is equal to my left force, right? And if we kind of just solve this, we'll see that, well, my tension along the cable, the first cable is equal to my tension along the second rope in the x direction. So we know that all my forces in the x direction are balanced. The cable is in equilibrium, which means that the forces in the x direction are balanced. So now we have to figure out, well, how do we get T2x, right? How does one get the tension of the second rope along the x-axis? Let's look at our y-axis. So let's take a look at all our forces acting the y-axis. Right, so I have my tension upward, which is essentially T2y, so that's tension of the second rope along the vertical axis, minus my force due to gravity. And my force due to gravity here is 50 newtons, right? That's my weight. So I'm just going to plug things in. My force due to gravity is my weight. It's 50 newtons. And so if we add 50 to both sides, well, this is what we get, right? So we can say that, well, my tension along the along the y-axis, right? They're equal, which means my tension of the second rope along the y-axis is 50 newtons. But we have to use trig, right? For us to get T2x, we must use trig here. And the formula we're going to use here is tangent. So tangent theta, right? Remember, tangent is opposite over hypotenuse. Oh, right, I'm sorry. It's opposite over adjacent. Opposite over adjacent. Right, so opposite over adjacent. My opposite here is T2x, right? That's my opposite. And my adjacent would be to the angle, right? In reference to the angle itself is T2y. So tan 20 degrees is equal to T2x times over T2y, which would be 50 newtons, which we saw above. So we have 50 newtons above, so 50, 10, 20. Right, so the tension along the x-axis here, along the second rope, is 50, 10, 20. So let me pull out my calculator. We just do some 50, 10, 10, 20. 50, 10, 20. And we get 18.2. We get 18. 0.2 newtons. And so this is my horizontal force, right? So this is my horizontal force along the x-axis. And if we go to my net force along the x-axis now, we know that T1 is equal to T2x. So we know that T1 is equal to 18.2 newtons. And that's our answer there. That's our answer. All right, let's go to I. So a rod is free to slide on a frictionless sheet of ice. On one end of the rod is lifted by a string, and the rod is at rest, which diagram in the figure below shows the correct angle of the string. If you kind of think of real life, right? If you think back to real life, if you kind of just hang a string here, or use a rope, and then you have something hanging there, well, this object really won't move, right? Right? If you kind of pull a book at an angle and you hold the book at an angle with the string, the book won't move. And that's what happens in real life. Well, that happens because the book is prevented from moving because of friction, right? Sure, you might be trying to move it that way, but there's friction acting in the opposite direction. The tension along this rope here is split into a vertical axis, right? So there's tension in the y-axis, and there's a tension along my x-axis, which means that there's a force along my x-axis to the left. And because there's no friction in this problem, well, there is no counteracting force to kind of make it kind of put it in equilibrium. And because there's no counteracting force, there's no counteracting friction force, this rod will keep moving to the left until the rope kind of just looks like B, right? Because if you take a look at B, your tension force is only along the y-axis. There's no tension along the x-axis here, right? There's no tension along the x-axis. And then the same thing with C, right? So there's a tension along the x-axis and a tension along the y-axis, and this rod will keep moving to the right, well, because there's no counteracting force to the left, right? There's no friction here, right? There's no friction. There's only a force to the right. So B is the only correct diagram here that kind of shows you what would happen if for the object to be at rest, right? Let's look at a J, right? Let's look at a J. So a car with a mass of 1,500 kilograms being towed at a steady speed by a rope held at an angle above from the horizontal. A frictional force of 320 newtons opposes the car's motion. So the car is traveling at a steady speed. Right? The car is traveling at a steady speed, which means that, well, my net force acting in the x direction here is zero. And we can say that, well, all my net forces acting in x direction, well, there's a frictional force acting to the left. But your tension force here, the tension along the x-axis, this tension along the x-axis is equal to, again, this side here is adjacent to your angle. I will put my hypotenuse tension adjacent, which is cosine, right? So cosine is adjacent, 20 degrees. So my horizontal vector in the positive direction is T cosine 20 minus my force due to friction, right? Because my force due to friction is acting in the opposite direction. My force due to friction here is 320 newtons. So I can say that, well, we'll start replacing 0. So 0 is equal to T cosine 20 minus my force due to friction, which is 320 newtons. I'm going to add 320 newtons to both sides, right? So 320 newtons, T cosine 20. I'm going to divide cosine 20 on both sides. And then I get T is equal to 320 divided by cosine 20. Okay? So, and then I get 341 newtons. And this would be my tension in the rope. Right, that would be my tension in the rope. Let's do AK. Let's do AK. So a ball of weight 200 newtons is suspended from two cables, one along the horizontal and one at a 60-degree angle. And which of the following must be true of the tension at the angle table? Of the angle cable. So again, you know that. Well, let's take a look at our y-axis. So our total force along the y-axis is 0. So essentially we're taking the tension of the vertical tension y here. And we also know that, well, this angle is the same as this angle over here. So these two angles are equal. So Ty in reference to this angle is opposite. So I will use sine. And again, I was always lead with the hypotenuse, which is tension, and followed by the sine because it is opposite. So sine 60. T sine 60. So my forces along the y direction is T sine 60 minus my force due to gravity, which is again is my weight. So I have 0 here. T sine 60 minus 200 newtons. Well, get rid of the newtons, right? You don't really need to put the newtons there. Plus 200 plus 200. So 200 is equal to T sine 60 divided by sine 60 here. And then your tension is 231 newtons, right? So your tension is 231 newtons here. So your tension, the answer here is A. Your tension is greater than 200 newtons. All right, that's it for these problems.